Hello, this is SST Chemistry YouTube channel welcoming you for the 15th lecture on stoichiometric calculation. I mean basic concepts in chemistry, and this is the third part of reaction stoichiometry, and that is on a very important aspect of stoichiometry. That is what we call POAC, Principle of Atom Conservation, POAC. And how fascinating it is, a concept to use in solving stoichiometric problems. You will see today. Of course, this is not a new technique, it's the same one, but used to simplify the calculations. This is another technique to make stoichiometric calculations without balancing equations. You can sometimes bypass the balancing step if you follow the POAC method, principle of atom conservation, right? It's also based on the principle of conservation of mass. It's not deviating from the conservation of mass principle. Hence, conservation of moles and atoms of each element during the reaction is there. So, in a reaction, since the mass is conserved, the number of moles and hence the number of atoms of each element are also to be conserved. This is alternative method for balancing simple reaction equations. You can also use this POAC concept to balance equation, but nobody uses that method. This is used for solving stoichiometric problems, numericals, not to balance. But by this approach, we can solve two simultaneous reactions representing in one equation. In balancing equation method, we were writing two equations separately and calculating separately and then adding up and whatever. But here, if both the reactants give the same product, then we can put them, both the reactants, in the same equation. Need not have to balance it. For example, you have a sample of calcium carbonate, magnesium carbonate. Earlier, we were writing two different equations, one for the decomposition of calcium carbonate, other for magnesium carbonate. And when we were analyzing the sample, we were taking x1 minus x or 2 minus x. So here we can put both calcium carbonate and magnesium carbonate in one equation, and we will see how calcium atom and magnesium atoms are conserved in the reaction. Right? We'll see large number of examples we shall take. And we can also miss out water, some H plus ion, OH minus ion, all these details we skip, not required, because we are basically interested to monitor the fate of a particular element. It is going from here to there, so we are following, and its number of moles of atoms or number of atoms is not going to change. That will make the mass fixed, right? So in a very easy way, we can solve these stoichiometric problems without inviting trouble. It is a powerful method of chemical calculations when large number of successive reactions are involved to synthesize a compound where a particular element present in the reactant, that means the starting material, is also present in the final product, and is not shared or disproportionated to form other products. In such case, it is the best method because you are bypassing the intermediate steps. You are taking the first starting material and the final product, correlating between these two species because they carry the common element, and the conservation of that particular element, the number of atoms, that will fetch you answer or the correct analytical answer within no time. Just have a look. In some analysis, the POAC concept is more uneconomical than the balanced equation method. So you have to judiciously decide whether you are going to use the POAC method or the normal balancing equation method. It's not that you learn a very interesting and powerful method of solving problems, that is POAC. That doesn't mean that you will apply that method in solving all problems, all numericals. You will yourself feel after you pass through this lecture and solve the assignments, you will feel where you will put or use the POAC method or not. So you will not be, biased by POAC method. Know its limitations and great advantages. Use judiciously. Now see, the number of atoms of each element remain the same during the reaction. That leads to conservation of mass, number of atoms. Hence, the number of moles of atoms of each element in the two sides remain the same. Note that the number of moles of substances, that is reactants and products, may not be conserved, and in fact, in most of the reactions it is not. But in every case, the number of moles of atoms of each element is conserved, has to be conserved, because the mass has to be conserved, right? For example, here N2 plus 3H2 gives 2 ammonia. So in the left side there are 4 moles and it is transforming into 2 moles. So there is no conservation of the number of moles of the substances, reactants and products. But if you look to the individual elements, there are 2 moles of nitrogen atom here, 2 moles of nitrogen atoms here, 6 moles of hydrogen atoms here, 6 moles of hydrogen atoms there. So always in a reaction, the number of moles of atoms of each element is conserved, but not necessarily the number of moles of the reactants and products. By chance it may, but in most cases it doesn't. Now, for example, let us try to learn how we can apply the POAC concept method to solve problems. And we will feel for ourselves that this numerical is not to be handled with POAC, rather than balance the equation in no time and solve the numerical just within a second, below the symbols, the formula of each substance, each reactant and product. Say, this decomposition of KClO3 giving KCl and oxygen, this is, let us try to apply the POAC. We are not balancing it. In POAC, the reaction equations are not balanced. Now let us apply oxygen POAC. Each individual element has to be taken separately. So let us try to apply POAC to oxygen element. And you see, in one molecule there are 3 atoms. So whatever number of moles of KClO3 you will be given, in your analysis, that multiplied by 3, because 1 mole contains 3 moles of oxygen atoms. So X mole will be containing X into 3 moles of oxygen atom. On the left side and in the right side, there is no oxygen here, so nothing is to be written for this, but here there is oxygen. So the number of moles of oxygen into 2, because one molecule contains 2 atoms. So this atomicity, number of atoms present in that of that element in this compound, has to be multiplied here. 3 has been multiplied here, 2 has been multiplied here. So to write once again, number of moles of KClO3 into 3 is equal to number of moles of oxygen into 2. Show the mole ratio, KClO3 and O2, the mole ratio is 2 is to 3. Let's apply POAC to potassium element. The number of moles of KClO3 into 1, because this formula contains 1 atom, is equal to number of moles of KCl also into 1. There's no potassium here. So the ratio between potassium chlorate and KCl is 1 is to 1. So let us make it 2 is to 2, because we have to correlate between all the reactants, the reactant and both the products. And just to find out, just to know that this is another method to balance, to know their stoichiometric coefficients, we can also use this method. But we never use this method. Only to solve problems, yes. Now see, KClO3 is to O2 is 2 is to 2. 2 is to 3. KClO3 is to KCl 2 is to 2. So 2 is common for KClO3. We have made it deliberately so that the ratio between KClO3, KCl and oxygen is 2 is to 2 is to 3. So that 2, 2, 3. So we can get the coefficients in the balanced equation by this method also. Now let us solve a problem. The same reaction. What mass of oxygen gas will be produced by the complete decomposition of 12.25 gram of KClO3? Now, the reaction is this. Once again, I am writing, and no need to balance it. And let us first go for oxygen POAC. The number of moles of KClO3 into 3 that is equal to number of moles of oxygen into 2. This N stands for number of moles. But let's find out from the data what is the number of moles of KClO3. So the number of moles of KClO3 is the mass by its molecular mass, which is 122.5. The number of moles is 0.1. So if this is the relationship, 3 into number of moles of KClO3 is equal to 2 into number of moles of oxygen. So since this is known, so number of moles of oxygen is equal to 3 by 2 into number of moles of KClO3. So this is 1.5 into this has been already, you have got it, 0.1. So the result is 0.15. So the number of moles produced is 0.15, and hence its mass will be number of moles into molecular mass of oxygen is 32, so 4.8 grams. Had you been asked how much of KCl would have been obtained, then you would have used KPOAC. You are not asked here, but supposing you would have been asked, find the mass of the residue. So you would have applied POAC to K element. So the number of moles of KClO3 into 1, because there is 1 atom in the formula, is equal to, in the right side there is no potassium here, number of moles of KCl also into 1. So number of moles of KCl is same as the number of moles of KClO3, because there is no potassium in any of the products. So that is also equal to this one, potassium chlorate, number of moles of potassium chlorate, and the mass will be immediately, this is number of moles of KCl, is also equal to 0.1, because this is 0.1, so this has to be 0.1. So to converting into mass, so you have to multiply by its molecular mass or empirical formula mass. So this is 7.45 gram, right? So let's take another example where we will apply the POAC to all the elements, all the three elements present, because you are asked to find out the masses of all the elements excepting all the substances, excepting the one the data is given for carbon dioxide. What mass of ethanol on complete combustion will form 11 gram of CO2? What mass of water be formed, and what mass of oxygen is consumed? Now let us write the combustion equation of ethanol, giving CO2 and water, and make sure that you are not going to balance. So in POAC method, balancing is spontaneous. We are in fact going to balance it, but we will not write the coefficients. Instead, we will solve the problem, right? Now, the data is the number of moles of carbon dioxide. So the number of moles of carbon dioxide, let us first find out. That is mass by molecular mass, 44.25. Let us first go for carbon POAC. Carbon is here, nowhere else. So the number of moles of ethanol into 2, number of moles of carbon into 1. Then the element carbon is conserved. Now, since the number of moles of ethanol is known, so the number of moles of number of moles of carbon dioxide is known, so number of moles of ethanol is equal to half into number of moles of carbon dioxide. So that is 0.25 into half, that is 0.125 is the number of moles of ethanol, and immediately you convert to its mass by multiplying with its molecular mass. So the mass of ethanol is 5.75. Again apply POAC to hydrogen element. Now hydrogen is present here and here, not here and here. So number of moles of ethanol into 6, because in one molecule there are 6 hydrogen atoms, right? So into 6 is equal to number of moles of water into 2. Here there are 2 hydrogen atoms, here there are 6 hydrogen atoms, right? So from here we know the number of moles of water is equal to 6 by 2 into number of moles of ethanol. So number of moles of ethanol we have already got, so multiplied by 3 will give you the number of moles of water, and to convert to its mass you multiply by 18 to get the mass of water formed is 6.75 gram. And again we have to apply the POAC to oxygen POAC. Oxygen is present in more than one substances. In left side both ethanol and oxygen, and in the right side both carbon dioxide and water. So to apply the POAC to oxygen is the number of moles of ethanol into 1, number of moles of oxygen into 2, and in right side number of moles of carbon dioxide into 2 into 1, number of moles of carbon dioxide into 1. Here I have done a mistake, I'm so sorry. So here we have to correct it, number of moles of carbon, it's okay, because we are not applying POAC to carbon, we are applying POAC to oxygen. So there are 2 oxygen atoms, so into 2, that's okay. So number of moles of carbon dioxide into 2 and number of moles of water into 1, because there is one oxygen atom. So both the number of moles have been found out. One is data is given 0.25 carbon dioxide, and we just now found the number of moles of ethanol 0.125. So use them, and the only unknown here is the number of moles of oxygen that we get to 0.375, and converting it into its mass we get 12 gram. Right? Now let's compare how long it will take to solve this problem by normal balancing method. I mean, first you balance this equation. You may spend some time here, because I think for this equation balancing will not take any extra time, because this inspection can help you in finding the coefficients. And then write the molar species, molar masses with their coefficients, 1 mole 46 gram, 3 moles 3 into 32, 2 moles 2 into 44, 3 into 18. Then this data is given. So for these two, leftwards calculation, and for this, rightward calculation. Right? So if this is produced by this much, so 11 is produced by this divided by this into 11, 12 grams. So if this much of carbon dioxide is produced by this much of ethanol, then 11 gram will be produced by 46 by this into 11, right? So if this amount of carbon dioxide is produced when 3 into 18 grams of water is also produced, so 11 gram of CO2 will be produced when 3 into 18 divided by this into 11 gram, that is 6.75 gram of water is produced. So in one go, just by writing the balanced equation and writing the molar amounts, we then find out what is the actual amount that will be involved in our experiment. Right? Which method you liked, particularly when you are given this problem? Which method you will apply? Tell me honestly, whether POAC, for getting water, you have to go till end, oxygen POAC. But to find the amount of ethanol, only carbon POAC will make your purpose fulfilled. But if you want to know how much of oxygen is consumed, yes, how much of oxygen is consumed, then I think we have done how much of, yes, here. For that we have to apply the POAC for oxygen. At the end we have to, because oxygen is present in both the reactants and both the products. So let me tell you that whenever you find that an element is present once in a reactant and once in product side, then you apply POAC to that element which appears once in the left side and once in the right side, and then find the number of moles of the unknown, I mean the one which data is not given. And then at a later time you go for the element POAC which appears more than once in both the sides or in one side. In the previous example, first we applied POAC to carbon and hydrogen, because carbon appeared once, that is ethanol, and in right side also once, carbon dioxide. Similarly, hydrogen appears once in ethanol and once in water. Finally, we applied POAC to oxygen, because by that time we have already known the number of moles of ethanol. Right? And by applying, I think we haven't applied the POAC of hydrogen. POAC, yes, we have applied, yes. To find the number of moles of ethanol, we applied POAC of carbon. To find the number of moles of or mass of water, we applied POAC of hydrogen. Then finally, knowing the number of moles of water and number of moles of ethanol, we applied POAC to oxygen element and got the mass of oxygen consumed in the reaction, right? Let us start. See, let's take another example where the reactant gets disproportionated, oxidized as well as reduced. Sometimes to go for a calculation for such type of reactions, we have to spend a lot of time in balancing. Really, it is time consuming to balance a disproportionation reaction. I hope you know what is a disproportionation reaction. The same element gets oxidized as well as reduced. Now, for those such reactions where in which you already remember the coefficients, there is no problem. But those other ones whose coefficients you do not know, you have to find out in the examination or when you are solving the problem, then you may spend some time by using some method, ON method, oxidation number method. And in that, the electron balanced diagram method you may take up using pen and paper to find out the total, the net electron balance diagram, and then looking to that, you balance. You may have to spend some time. But in POAC, balancing is inherent. In fact, we are going to balance by POAC method, but we are not finding the ratio so that we can put them in the equation to balance it. Our job, our motives, our objectives will be fulfilled by equalizing the number of moles of each element, number of moles of atoms of each element. I repeat, the number of moles of atoms, right? So, in this reaction, hypophosphorus acid is heated to produce phosphoric acid, that is orthophosphoric acid and phosphine gas, right? So it is asking what mass of this on heating will produce 3.4 gram of phosphine. What is the mass of the other product? Solve both by POAC and by usual method and see the difference which you like. In some cases, you will have a clear understanding, visualization that yes, I have to use this, I have to solve this by POAC. And in some others, no, POAC is not suitable. It is rather more time consuming, right? Now see, this is the unbalanced equation. Let us apply POAC to phosphorus. Now let us first find out what is the number of moles of phosphine present in 3.4 grams of it. 3.4 by its molecular mass is 34. 31 plus 3, 34 is 0.1, right? So then phosphorus POAC, number of moles of this into 1 is equal to number of moles of this into 1 and plus the number of moles of this into 1. So supposing, let's take X is the number of moles of this and Y is the number of moles of this. So you get an equation X is equal to Y plus already phosphine, the number of moles is known 0.1. So X is equal to Y plus 0.1 is one equation. Let us apply the POAC to hydrogen element. So number of moles of this into 3 is equal to number of moles of this into 3 plus number of moles of phosphine also into 3. So this is 3x, this is 3y, and phosphine again is 0.1, 3 into 0.1, 0.3. So dividing by 3, you are getting x is equal to y plus 0.1, the same relation that we already have got. So this particular equation will not help anyway because it is a repetition. It is a repetition. So by applying POAC to hydrogen, we didn't gain anything. So how to gain? So only element left is oxygen. Let us apply POAC to oxygen. The number of moles of this into 2, because there are 2 oxygen atoms, is equal to number of moles of phosphoric acid into 4. So here 2x is equal to 4y. So x is equal to 2y. So this is another equation. So we have 2 equations. We can use x is equal to 2y here, putting x is equal to 2y, and then we get y is equal to 0.1. And once we know y, then we can put in any of the 2 to get x. X is 0.2. So immediately convert the number of moles into mass. Since x is S3PO2, so this is 0.2 into the molecular mass is 66. So 13.2 grams of this. And 0.1 is y, that is phosphoric acid product, and its molecular mass. So 9.8 grams of phosphoric acid will be formed. So I think you could have done, had you remembered the coefficients, these 3 coefficients, then it is easier by the previous method, normal method. I will call it a normal method of solving problems, stoichiometric problems, by taking the balanced equation. But the POAC concept is also applicable to all. But in some cases, it will be more time consuming than the conventional method. So here, we could have solved this problem had you balanced this equation easily. We know the coefficients easily, or you have memorized, or if you take some time, by that time, you can use POAC and get your answer. Now see, normal method, since we know the coefficients 2, 1, 1, so this is a simple equation, simple disproportionation, 6, then 2 into 66 gram, 34, 98. So this data is given, so we go rightwards to phosphoric acid, this by this into this, 9.8, go leftwards, this divided by this into 3.4, so same answer we get. But balancing equation may take some time in disproportionation. Here it is an easy one, but in others you will find, if you have not remembered the coefficients, then you take some time, quite some time. Less than that time will be required for solving the problem by POAC. Now let us solve this problem. Diphosphene on decomposition gives, this is the diphosphene gives phosphine plus P4H2. We can call it tetraphosphine. So this decomposition, this equation needs a lot of time to balance. First we have to find out the electron balance diagram, then balance. So forget about this. POAC is the most suitable method. Now, since the amount of diphosphene is given, so we can find out the number of moles of diphosphene is equal to 0.66 by 66. Because 66 is its molecular mass, you can find out 31 into 2 plus 4. So this is 0.01 mole. So the number of moles of diphosphene is given, the reactant. So we can go for there are only 2 elements, so one for phosphorus POAC, the other one is for hydrogen POAC. I have done it to save time. Now we applying phosphorus POAC, the number of moles of diphosphene into 2, here find 2, and the number of moles of phosphine into 1 plus the number of moles of tetraphosphine P4H2 into 4. So we have, supposing the number of moles of phosphine is X, the number of moles of tetraphosphine is Y. So we get an equation. This is known. 0.01 into 2 is equal to, this is X plus 4Y. This is one equation. And let us build another XY equation with hydrogen POAC. In hydrogen POAC, the number of moles of diphosphine into 4 is equal to number of moles of phosphine into 3 plus number of moles of tetraphosphine into 2. So again, this is known. We get another simultaneous equation involving X and Y. So solving them, by solving these two, we get X is equal to 0.012. What was X? X was phosphoric acid. X was phosphine. And Y was, tetraphosphine. There is no phosphoric acid. That's a slip of my tongue. Phosphine is X and tetraphosphine is Y. So we got first X is equal to this. And Y we have got first 0.002 and X is equal to 0.012. So we have converted into their masses. So this into 34 is its molecular mass, and this into 128 is its molecular mass. We got their masses, right? So I think for this POAC method is more suitable than balancing, because balancing you will lose more time, right? So even just for fun, let us know this method can also be used to find the coefficients, or that is to balance the equation. Supposing we want to balance this equation, ABC3 gives AB plus C2. A, B, C are three different elements. Now by inspection method we can do it here. Here it is 3, here it is 2, so we multiplied by 3 here, 2 here, so C is balanced. So then when 2 here, then we also make 2 here. So 2, 2, 3. So by inspection we can balance this equation. But I wanted to tell you that the POAC method, we can find the coefficients, and that is to balance the equation. For example, if you apply POAC to A, element A, then number of moles of this into 1 is equal to number of moles of this into 1. There is no A here. So the ratio, mole ratio between these two is 1:1 or 2:2. I made it 2:2 to equalize in other ratios having the same substance. So applying POAC to B, it is number of moles of this into 1, number of moles of this into 1. So the ratio between this reactant and AB is 1:1. That is 2:2. Then let us go for the POAC of C. So in the POAC of C, then the number of moles of the reactant into 3, there are 3 C's. Number of moles of AB into 0, because there is no C here. I should not have written that. And in the last product, that is second product, number of moles of C2 into 2, because there are 2 C atoms. It's not carbon, C atoms. C is an element. So here the ratio between this and this is 0. Let us remove from. So the mole ratio between the reactant and C2 is 2/3. So 2 is common. This is 2, this is 2, and this is 2. So therefore, the ratio between the moles of this and this is 2:2, 2:2, 2:3. So 2, 2, 3. So I wanted to just tell you that this is indirectly yours going to balance this equation. So the POAC is nothing but conservation of mass. Let's solve a problem. A mixture of KBr and NABr both contain bromide weighing 0.56 gram was treated with aqueous silver nitrate solution to form 0.97 gram of pure and dry silver bromide. What is the mass fraction of the KBr present in the original mixture? Right? So earlier we were writing two separate equations, one for the reaction, because these are two simultaneous equations, right? So this was giving the yellowish white precipitate, and we were balancing it. It is already balanced, and NaBr we are writing another equation to give you same product AgBr plus NaNO3. So then we are solving, taking this as x, then finding what is the amount of AgBr, and this taking as something minus x and finding what is the mass of AgBr. Then we are adding together and equating to the mass of silver bromide produced. So it was time consuming. Instead of that, we can put the two reactants together in one simple equation. And this is more algebraic equation than a chemical equation. So our purpose is to find this stoichiometric relationship, not to ensure what is the real happening. So we can put KBr and NaBr in same equation with the reagent nitrate, silver ion. We can also put this as silver ion, doesn't matter, to give you silver bromide as the insoluble precipitate, sparingly soluble precipitate, plus K plus Na plus. So our concern is for silver bromide, which is produced from both sodium bromide and potassium bromide. So we have to trace this element. Only bromine POAC will solve the matter, because bromine is present in only one product. I told you that if an element is present only once in a particular site, then it will be easier for us to handle. Now let's apply. Supposing this amount is x and this amount is 0.56 minus x, because the total is 0.56, and the number of moles, supposing bromine POAC we will do, then number of moles of KBr will be x by its molecular mass. I have done it to save time. Supposing this is x gram, this is 0.56 minus x gram, and this, the total silver bromide formed from both is this much, right? So x, its molecular mass is 119. So because 80 plus 39, so that moles into 1, because there is one potassium atom, and about one bromine atom. We are going for bromine POAC, one bromine atom. So the number of moles of KBr into 1, the number of moles of NaBr, that is 0.56 minus x, by the molecular mass of NaBr is 103 into 1, because there is one bromine atom also here, is equal to the actual number of moles of AgBr is 0.97 by its molecular mass, 108 plus 80 into 1, there is one single bromine atom. So we are applying POAC to bromine. We are not concerned with any other element. Our situation, our numerical, our problem demands that we focus only on bromine. So bromine POAC is applied. So by solving this, we get only one, x is the unknown, we get x is equal to this many gram, because we have taken x as gram. This is mole. So x is taken in mass. So directly we get the mass of KBr, which is this much. So mass fraction of KBr is equal to the individual mass by the total mass into, not into 100, it's fraction. So the individual mass by the total mass will give you the mass fraction, and if you multiply by 100 you get mass fraction. It is 37.9%, but the question is demanding mass fraction. Now let's see, this looks to be a huge molecule, but don't be scared at all. Once you are conceptually strong in POAC, then you will ignore whether it is going through 2 steps or 3 steps or multiple steps. For example, what mass of kaolin, which is an aluminum silicate, hydrated aluminum silicate, will produce 10 gram of aluminum sulfate dot 8 water. It's a huge molecule. This is a huge molecule. But in some synthetic sequence, not given to you, assume that all aluminum present in the kaolin mineral is also present in the aluminum sulfate synthesized. So that is the presumption you have to make, and that is not a wild presumption. It is an acceptable assumption, because aluminum will pass on in series of reactions to form aluminum sulfate, and aluminum doesn't undergo disproportionation, right? So it's the transition element, or some non-metals which can go higher, go lower, they can disproportionate. So here we will presume that all aluminum present in the kaolin, in the starting material, will also be present in the final product. Now see. Let us write down a representative equation. It's not a full chemical equation. We are just planning the schematic representation to give you Al2SO4 whole 3 dot 18 water. That is after crystallization, right? So we have to correlate between this and this. Here it is 2 water, it is 18 water. Doesn't matter. Aluminium is to be conserved here. So the number of moles, supposing of this huge compound is X into 2, is equal to here also 2. So supposing the number of moles of this huge compound is Y into also 2. That's it. I have done for you. Have a look. So the number of moles of kaolin, which is a silicate mineral, and in the final product there is no silicon, it's gone. In other products we are following the conservation of aluminum element. So number of moles of kaolin into 2, because there are 2 aluminum atoms, and this N is the number of moles of this hydrated aluminum sulfate into 2. There is also 2 aluminum atoms. I'm sorry. So 2 to get cancelled, and you are getting this number of moles of the kaolin is same as the number of moles of hydrated aluminum sulfate. But from the data, let us first find out what is the number of moles of aluminum sulfate. 10 I'm sorry, is divided by the molecular mass of the huge compound 666. I have got it. So the number of moles of kaolin is also same, 10 by 666. Right? And hence, to convert into the mass of kaolin, we have to multiply with the molecular mass of kaolin, which I have found out to be 258. So the number of moles of kaolin is 10 by 666 into the molecular mass of kaolin. This is a huge molecular mass. That is giving 3.993 grams. So is it not interesting? For such analysis, particularly POAC is mind-blowing method. Correlate between the starting material and the final product. If you are sure that a particular element is percolated in these different steps and finally is present in the final product, right? You will definitely have some confidence to presume this after we solve some problems. Now this is another one, very, very similar, where you are handling with a huge compound. How many moles of nitroglycerin? Nitroglycerin having formula this huge, when explodes, produces 11.2 liters of carbon dioxide at STP. Assume that all carbon present in nitroglycerin is also present in the final product CO2. Now see, This is nitroglycerin. The formula is given. It will be converted to CO2. You need not write the entire equation. In fact, we do not know whether some other reactant is involved, say oxygen is involved in the explosion, or simply on heating it undergoes decomposition. We do not know, and we are not supposed to know, because we are not interested in following oxygen. We are interested in how much of carbon dioxide which is present only in CO2. If I give you the actual happening here, what happens to nitroglycerin, just for our curiosity, if you want to know what are the products formed, then I have the data just to show that this is not required. Doesn't matter, I didn't get it. We're not supposed to remember all happenings during a reaction. So, doesn't matter at all. Okay, so we are not interested in knowing that. So what happens here, the number of moles, supposing of this huge compound is X. So X into 3, there are 3. And this is carbon dioxide, number of moles is given. 11.2 means half mole. The molar volume is this. So into 1. So by solving, you can get X is equal to 0.5 by 3. The number of moles of this huge nitroglycerin is 0.1, I have already done 167 moles. And to convert into its mass, it's easy. But have you been asked about, now find the number of moles of nitroglycerin, not mass. So this moles, got it, right? Here also a similar kind of thing. I think you can do of your own. It's already 53 minutes. 0.1 mole of calcium phosphate was converted to phosphorus element by reacting this rock phosphate, the calcium phosphate, with silica and coke and heating the mixture. Then the phosphorus obtained from this is further is allowed to react with concentrated nitric acid to form phosphoric acid. Assuming that all phosphorus present in calcium phosphate is also present in phosphoric acid, the final product. So calcium phosphate is the starting material, and we are getting final product is H3O4, where phosphorus is percolated throughout. So here there are 2 phosphorus in one molecular formula, and it's 1,1. So supposing the number of moles of calcium phosphate is given 0.1. So 0.1 into 2, because phosphorus atoms is 2, is equal to, supposing the number of moles of phosphoric acid form is X, into 1. So it will be 0.2. So number of moles will be just 2 times, because there is 2 here, it will be 2 times, then only it will be balanced, right? So to convert into its mass, it's just simply multiply by its molecular mass, 98, and we get the mass of phosphoric acid formed is 19.6. So this is a mole mass relationship problem, but instead of writing all the steps, we do not know Or even if we know, we bypass because the same element is throughout present until end. And we believe that the reaction is 100% complete. There is no need to find the theoretical yield, the yield of this reaction. Now, here is also another where you have both reactants, which is ferrous oxide and ferric oxide. When the mixture of this, when heated in air to constant mass, gains 5% in mass. Find the composition of the mixture. Given that in the reaction, both reactants produce ferric oxide. Ferrous oxide is also oxidized to ferric oxide, and this is magnetic oxide or ferroso-ferric oxide is also oxidized to ferric oxide. So earlier we were writing two independent equations, taking x for the first and this minus x for the second, and then adding up the total product in terms of x and then equating to the given data. Instead of doing that, here we can put both in same equation and forget about whether oxygen is taking part or not. Yes, it is taking part because both are oxidized, means oxygen is required. So it is giving Fe2O3. Forget about balancing. And simply because it is saying that both the reactants produce the same product. So let us go for FePOAC. That is the number of moles. Supposing we take 100 grams. Let us analyze. That is sometimes easier to take 100 as the total mass if you are following a percentage analysis. So out of 100 grams, supposing X is this, and 100 minus this, 100 minus X is this. So number of moles of APO is X by its molecular mass. That is 56 plus 16. Into 1, there is one atom, plus the number of moles of Fe3O4 is 100 minus X is the mass divided by its molecular mass. I have already found out it is 232 into 3, because here there are 3 atoms, is equal to the number of moles we do not know, number of moles of Fe2O3 into 2. Right? And that is equal to this is one relation, and constant mass gains 5% in mass. So it was 100 in the beginning, now it is 105 because we have taken 100 as the initial mass. So 5% is now the total mass is 105. So what I have done here, that supposing this is X, this is this, and we have done this X by 72 into 1. This is 72, oh, sorry, 16. This is 16. Right? Into 1, this is equal to this. And why I made it here? Because number of moles is the total mass, that is 105 now. All the reactants has disappeared, and so it is 105 by the molecular mass of Fe2O3 is 160 into 2. So we take 2 cases as 100 because these two were 100, but now it is 105. It's a gain in mass. When heated in air, constant mass, because oxygen, all the gases will go out. Only the mass is due to the constant mass after heating is due to this Fe3O4. And we have taken 100 grams as the mixture mass. So we are least bothered about oxygen, what has happened to oxygen. We have taken 100 grams of this mixture. And when, it was all converted to Fe2O3 and it was dried, no oxygen, nothing, then the dried mass was 105 gram. So that is the mass of this, right? So by solving this, because this is the only x is the unknown, solving this we get x is equal to 22.2%. Because we have taken 100, so direct answer is in terms of percent. So FEO is 20.2%, so 100 minus this will give you the percent of Fe3O4. In the similar way, you can solve this problem. It's a huge problem, but once you read it patiently, with patience, then you can make out that this is an analysis problem where the same element is percolated throughout till end. So you apply the POAC between the first and last. Lead is treated with excess nitric acid to form lead nitrate, lead 2 nitrate. This solution was then treated with so many things. In hydrochloric acid, chlorine gas is bubbled with ammonium chloride. That will give you a very interesting compound. This is ammonium hexachloride of plumbate, right? So forget about its name. So you are asked to find out the maximum mass of this ammonium hexachloride of plumbate formed. It's a huge compound. In an actual experiment, if an actual experiment, a student could prepare only 2.28 gram of this compound, then what is the percentage yield of this product? Now see, I've done it. Lead is finally converted to this compound, a complex compound. So we correlate between the starting, the number of moles is given, it is number of moles is 2.07, but its atomic mass is 207, it's 0.01. And number of moles of lead into 1, number of moles of this huge compound also into 1, because there is 1 lead. So whatever is the number of moles of lead, same is the number of moles of the huge compound, 0.01. Then we can convert into its mass by multiplying with its molecular mass, 456. So the mass of this complex compound formed is 4.56. Got it? How simple. And the yield, because the ideal value, if it's 100% converted, all lead is converted into this, it is 4.56. Always we go up to this, but rarely you will find that the actual yield is less than the theoretically predicted yield. In that case, you'll be asked to find out the percentage yield. So percentage yield is the mass of the same compound that was obtained by that boy, by that girl, the student, divided by this theoretically predicted value for the 100% conversion into 100. So the amount and the percentage yield of this reaction, of this product, is only 50%. So this is another way, dimension analysis or factor analysis method. This is not a new method. It is a shortcut method of solving problems. But same balancing the individual equations, if it is a sequential steps, so many steps are involved and you are going till end, you can use POAC. Also you can use this dimension analysis, whichever is convenient to you. In most cases POAC is convenient, but in some it will be too messy if you use the POAC concept. Have a look. Supposing you are given this series of steps, starting where we are wanting to prepare polyethylene, the plastic polyethylene polymer, wherein is the degree of polymerization is huge and not fixed. So you are asked to find out the mass of the polyethylene that will be produced from 10 kg of the starting material, it is calcium carbide. We have to perform 3 steps. Calcium carbide is first treated with water to give you acetylene gas. Acetylene gas is reduced by hydrogen to make ethylene, and then there is a triple bond here, there is a double bond here. So reduction of acetylene forms ethylene, then polymerization of ethylene produces the polymer. right? These are the 3 steps, and you are asked to find the mass of this. So the conventional way is step-by-step analysis. Find the number of moles or amount of the product of the first reaction, use that in the second reaction, and then find the number of moles of the product of the second reaction, use that in the third reaction to finally find the number of moles of the final product. Then you can easily convert into its mass, right? What do? You write like this: 1 mole produces 1 mole. So these many moles produces how many moles? Then again, 1 mole is always better to follow by mole method rather than mass method. Mole is versatile. Mole is versatile. So again, 1 mole gives 1 mole. So whatever mole we have got here, that many moles will give how many moles? And then n moles gives 1 mole of this polymer. So whatever number of moles you have got here, that many moles will give how many number of moles? So number of moles will get in terms of n. The moment we find its mass, the molecular mass also has an n term. They will cancel out and you get finally a digit not involving n. Let's see. So what is dimension analysis? You write only the dimensions in a single line. Don't follow up, the procedures, these unitary method procedures and consume a lot of space to do the same thing. So what is here? I have done it here. So the mass of final product, that is polythene, is equal to, this is the number of moles of the starting material, that is calcium carbide. So what I wrote, 1 mole calcium carbide by its molar mass into the actual mass is 10 kg, 10,000 gram. So if 64 grams is equal to 1 mole, then 10,000 grams is equal to 1 by 64 into 1000. I did the same thing. So this is the number of moles of calcium carbide. Then go for the reaction, first reaction. The number of moles of acetylene is equal to same as the number of moles of calcium carbide, because this is 1:1 relationship. So 1 mole of acetylene by 1 mole of calcium carbide into the number of moles of calcium carbide. Right? Just we do by unitary method. 1 mole gives 1 mole. So these many moles will give how many moles? So we have come up to this, the end of reaction 1, step 1. Then whatever number of moles we have got here up to this will be used for the second reaction. 1 mole, 1 mole. So 1 mole of ethylene divided by 1 mole of acetylene. Supposing had it been 2 here, had it been 3 here. So into the number of moles. So far we have found out the number of moles of acetylene, right? So we have gone up to this, the end of second reaction. Then go for the final polymerization reaction. N moles will give you 1 mole. So 1 mole will give you 1 by n, and these many number of moles into that. So 1 mole of polyethylene by n moles of polyethylene into the total number of moles of ethylene, this much. So we have come to the end of the third and final reaction, but we have got the number of moles of polyethylene. But we are going to find the mass. So ultimately, we multiply by its molecular mass. So the ratio will be like this, because molecular mass of this is 28 into n. 28 is the mass of the repeat unit, the molar mass of the repeat unit. But the entire polymer molecule into n times, 28 into n. Gram of polyethylene divided by 1 mole, that will be the mass, because 1 mole has a mass equal to this. So this is finally, so this n here in the denominator in the previous ratio and n here in the molar mass get cancelled, and we get final, the mass of the polymer sample that is produced is 4,375. So this is the same way, had we gone step by step analysis and finding the number of moles and using them in subsequent steps, same thing we got in a very shortcut method. So you see 1:1, 1:1, 1:1, 1:1, 1:n, 1:n. Right? This is the mole of the reactant. This is the final mass of the product, right? But see how easy it is to solve by POAC method. We correlated calcium carbide till the end. All carbon atoms present in the plastic, in the polyethylene, has come from calcium carbide. Because you see, in this series of reaction, carbon is provided by calcium carbide. This. So this carbon is percolated till end, right? So number of moles of calcium carbide into 2 into number of moles of the polythene into 2n. So here let us write number of moles rather than number of this. Let us make it n, number of moles. So the number of, but in the data, the number of moles of the starting material is given 10 kg, 10,000 by 64, whatever. Let it be like that. So the number of moles of polyethylene is equal to the n get cancelled. This is n. I'm sorry. Oh, n, because there will be repetition. So therefore I have written, instead of n, I have written x. So let us say number of moles, I say mole, number of mole, right? So number of mole of calcium carbide which is given is this. And then the number of mole of polyethylene is 1 by n. Is 2 get cancelled? So 1 by n into the number of moles of calcium carbide. N gets cancelled. Where? Tell me where. So no. Here up to mole there is n. 1 by n. Cancellation will be occurring at the end. So 2 get cancelled and 1 by n into the number of moles of calcium carbide, which is this. And finally, to get mass of polyethylene, we have to multiply by its molecular mass, 28n. So here n get cancelled and we get. So see how quickly we arrived at the result by POAC method. So there is another problem here. Calculate, there are 3 steps. Chlorine is first converted to this. This is disproportionated, KCl, KOCl. Then KOCl is further disproportionated, KCl to KClO3. And then finally KClO3 is further disproportionated to KClO4, KCl. In this type of reaction where disproportionation is occurring in multiple steps, we cannot use the POAC concept. We cannot simply use the POAC concept. Here the only choice is the dimension analysis or the conventional unitary method that you are quite familiar with, right? So this is a leftward, since the data is given for KClO4, so we have to go leftwards. 3 mole is produced by 4 mole. So at this many moles produced by how many moles? 4 by 3 into the number of moles. Let us go by number of moles, it's easier. Then KClO3, 1 mole is produced by 3, so that many moles will be 3 by 1 into that. Then KOCl, 1 mole is produced by 1 mole, so that many number of moles produced how many? Is produced by how many number of moles of chlorine. So the same thing can be written in dimension analysis from leftwards, starting from here. The number of moles of KClO4 is given here 100 by its molecular mass 138.5. So 1 mole of KClO4 by its gram molar mass into the actual mass given is 100. This is the number of moles of this final product. We are going leftwards. So 4 by 3. When you are going rightwards, when the mass of the reactant is given, you are finding the mass of the final product, then you go rightwards. The number of moles of the right by number of moles of left. But when you are going leftwards, the number of moles of the left divided by number of moles of the right into the number of moles of this product. This is the number of moles of KClO3. Let us go in this way. So 1 is produced by 3. So 3 by 1, 3 moles of KOCl or KClO by 1 mole of KClO3 into the total number of moles of KClO3 up to this. Then you have gone up to the second one from backwards. Third is over, second is now over. Then the first one. The 1 mole gives 1 mole. So 1 mole of chlorine by 1 mole of chlorine, right side first in the numerator. Left side in the numerator and right side in the denominator. 1 mole chlorine by 1 mole KOCl, that will be the total number of moles of chlorine. But to convert into its mass, we multiply by 71. 71 gram of chlorine by 1 mole of chlorine. So ultimately, we are left with gram. So all the units get cancelled. So we get 205.04 gram of chlorine will produce 100 gram of KClO4. This is not POAC. POAC has its limitation. I have told you exactly. I have shown you where we cannot use POAC because every reaction, all the 3 steps are disproportionation reaction. So we cannot trace chlorine from start to finish. So this chlorine is not present in this. It is, spread into several compounds. We cannot say this chlorine has been obtained from this. This you cannot do. If you do, then have a look. What will happen to us? Supposing we forget to use this dimension analysis or the conventional method, we simply correlate all KClO4 has come from this. Then we need not have to balance. We should not. Simply write chlorine here, KClO4 here. So the number of moles of chlorine, say X into 2 is equal to the number of moles of this is already given, 100 by 138.5 into chlorine is 1. So the number of moles of chlorine will be equal to 50 by 138.5. So how much it is coming? So if you see, it is I'm just spending a bit of time with you to find 50 divided by 138.5, that is 50 divided by 138.5, that is giving 0.361 mole, and to convert into mass 0.361 into 71. It is coming 25.63. See, 25.63. Once again I tell you, this is 100 gram. This is 100 by 138. 100 by 138. So X is divided by 2 here. So this will be 50 by 138. So that is coming 0.361 mole, and it is converted to mass. It's coming 25.6. But while we are getting 205 gram of KClO4 really, but in this method you are getting, because chlorine has been distributed in so many products, so we cannot say that all chlorine which was taken initially is present only in KClO4. So here is a limitation of POAC method. So to end up this chapter, this lecture, my take is, do not, let me clear this out of the way. I wrote all this. If I send this file to you for your reference, then you will be put to a lot of difficulties. It will be very, very confusing, right? So my take is, you have several weapons, deadly weapons to combat, to attack your enemy, but not necessarily that you will use all the weapons in all types of words. If a very weak opponent will fight with you, you'll be using very simple weapons that will solve better purpose. You will not use an invincible weapon, it's very deadly weapon to tackle or to topple down weak enemies. So this POAC concept is very, very fascinating, but is to be used with a lot of caution. With experience, you will definitely get that feeling where to use and where not to use. Then it will be easy for you to to fathom or to go to the chemical analysis in a confident manner. Bye bye.